A boy flies a kite which is 40 feet directly above his hand. The wind blows the kite horizontally at the rate of 20 feet per minute. This problem wants to know at what rate is the string being pulled out when the length of string is 50 feet. So the first thing I'm going to do is designate some variables to stand for some relevant quantities in this problem. For example, the problem is going to be based upon a right triangle. And this triangle could be considered to have a leg called A and another leg called B and a hypotenuse which I could call C. Now the length of leg A is going to stay fixed throughout the problem. The kite is always going to be 40 feet above the boy's hand. But one quantity that is changing is B, and C is changing as well. Now with some of these quantities, we can find their rates of change. For example, I could make a little chart of the rate of change for each of these important quantities. A is not changing at all as time goes on. A is remaining 40 feet. The kite is always 40 feet above the hand. Therefore, I would call dA over dt 0. So this tells us how the height of the kite is changing. We also want to know how is the horizontal position of the kite changing. This could be called dB over dt. And so in this case, if we had a coordinate system established in this problem, the person could be considered to be at the origin, and this could be a y-axis, and this could be an x-axis. So basically B is equal to the variable x. And so we could call this dB over dt, or else we could rename it if we wish, dx over dt. And this is going to be given by the velocity of the kite. It's 20 feet per minute to the right. You could describe a velocity by telling how fast it's moving. That's the speed. And then also tell the direction as well. And so dx over dt is the 20 feet per minute. The thing we're asked for is how is the length of the hypotenuse changing? I would refer to this rate of change as dc over dt. And this is really unknown to us currently. And the thing about it you could probably figure is that rate of change is not even going to be a constant in this situation. At first, the difference between a string being vertical and a string being slightly slanted to the right here, the difference between those lengths is negligible as the angle theta between them goes toward 0. But as we go farther and farther out, the difference between the lengths becomes more apparent. We can see here that if we drew like a little bit of a circle showing how this length, CI, would match with this length here, and look how much more string there is. So the rate of change of C is actually not constant in this problem. It's changing all the time. So you might be wondering, how could we ever come up with a relationship which describes how these rates of change are related to each other? And in order to do it, we just want to start with a formula, a geometry formula that's relevant to this situation. That formula is Pythagorean theorem. It's a formula that's relevant for right triangles, which is what we have here. So let's write the Pythagorean theorem. A squared plus b squared equals c squared. That would always be true in this situation, no matter how long c was. What we'd now like to do is differentiate this formula implicitly. So when it comes to a, b, and c, we could start with the default idea that they could potentially be functions of time, where any one of them could be changing with time. When it comes to A, I actually know that he is not changing with time. And that's significant in this problem. But B is changing with time. And so is C. Now, anytime we're taking a derivative implicitly, we're going to do the derivative on all the terms. But in this case, I'm going to take a derivative with respect to time so that I can get a sense of how these quantities are changing with time. And each one of them, we could just consider by default that they might be functions of time. The ones that are B and C. We can see that here and here, these quantities are going to be non-zero, whereas dA dt is 0. All right, so when we differentiate implicitly, we should take the derivative with respect to the variable in question, a, and then we'll multiply by, according to the chain rule, we'll multiply by dA dt. Here we're going to take the derivative with respect to b at first, and then we'll multiply by dB dt. I'll take the derivative with respect to c, making this 2c, but considering that c is really a function of time, we should also multiply according to the chain rule by dc dt. The idea that I used here was that if you're taking a derivative with respect to one variable of a function of another variable, then according to chain rule, I can do df over dA times dA over dt. Basically, we're saying that A itself is a function of time. So yes, I can differentiate this f with respect to A, but that's not good enough. I should also multiply by dA over dt to complete the chain rule. I did that for each of these cases. And now I have an expression where I can plug in the relevant quantities. I know what some of them are already. So A is 40 feet. That can be plugged in here. dA dt is 0. B is going to be something that we're going to have to calculate. We can do it with Pythagorean theorem on the side. And this is for a particular instant of time. Pythagorean theorem always holds at all times. But there's one value of B at a particular instant of time shown right here when the kite is in that location. And we need to find out what that value of B is. So I'll do a squared plus b squared equals c squared. The time in question is when a is 40 and c is 50. We can now solve take a square root. B is 30 feet at the time that I've drawn here. Keep in mind that B is going to be different values throughout the flight of this kite. It's only 30 feet at the point that they've asked us about, when A is 40 and C is 50. Now I'm going to plug that in. I'll now want to multiply by dB dt. That was given in the problem. Right here, it is the horizontal velocity of the kite, 20 feet per minute. I also wrote it here that dB dt was 20. Now I'll plug in C, which is 50 feet. That's the length of the string at the time described in the question. And what the question had asked us for was to tell the rate that the string is being pulled out. This is the thing that we're actually being asked for right here. dC dt. How is the length of this hypotenuse changing as time goes on? That is dC over dt. This could be considered a picture of dC right there. And so if we zoom in on that little piece right there, what are the differentials involved? So the change in horizontal would be considered dB or dx, and the change in hypotenuse would be considered dc. All right, let's now solve for dC dt and see what it is. So for my final answer, I get 12 feet per minute. So the rate of change of the hypotenuse and the rate of change of the string length across this diagonal at this point is going to be 12 feet per minute.